And now you can start from this.
Okay, well...
yeah, make applause to James, because he...
thanks for the introduction. This talk won't take 1 hour, but I just want to introduce myself. I'm at Czech Technical University, as some of my other colleagues are here. Like, we have a bit of a mafia here as well. And this work was done in conjunction with my colleagues Zuzana Kukelova, Ondro Holm, and Jiří Matas. So, what is it? Is it something going on? Okay, there. Yes, I see. So, as Vít said, I was here last year as well as Victor, and he cut our heads off and put them in a jar, but luckily it's reattached now. So I wanted to thank Vít for inviting me and having me here again. It's a pleasure. So what's going on here? Like, I don't. Okay. So this talk is about. It's actually mostly a geometry talk, so a little different, and we'll talk about some fairly trivial constraints induced by repetitive patterns in an image. This is single view geometry. So what's nice is that it'll be closed, and it's fairly easy to see, and they're simple. And so I think you might be impressed with such simple constraints, what you can actually achieve. And these constraints were derived by myself and our group. And in fact, there's been a lot of work on the inference side, but this is not the subject of this talk so much, but mostly just about what kind of constraints are induced by repeated patterns on a plane. And the patterns are everywhere. Of course, some of them are quite obvious, and some of them are a little more subtle. And I just wanted to show you some different use cases. We want to have a very general definition of a pattern. We can have translations, we have reflections, we have rigid transforms between the same repeat in the scene plane. We have several different types of patterns here on the same plane, some more reflections and symmetry, and rotational symmetries, reflections, etc. All of these can coexist. There can be one type, there can be many types, there can be multiple patterns on the plane, and we want to solve for these use cases. So a very general definition of a pattern, basically anything that's repeated by a rigid transform on a scene plane viewed by a perspective camera, even with lens distortion. So we'll talk about those geometric constraints, and I'll talk a bit about how to estimate those parameters. So a little motivation. Why do repetitive patterns cause problems with classical vision algorithms, or state-of-the-art even? And the issue is, well, I don't know how well you can see these blue lines here, but for example, let's take the epipolar geometry problem. So we have a two-view relation between two images, a left and right, a stereo pair. And if you estimate the two-view relation between this as a fundamental matrix, a fundamental matrix will transfer a point from the left image to a line in the right image. And Sasha talked a little bit a line search, for example, in reconstruction. Well, it's exactly what's happening here. So we might take some point here and it transfers to a line here. Well, if you're searching across the line, of course, in some naive way, you'll get many matches because there's repetitive structure there. And so you'll have many maxima, and you won't be able to select the correct one. And the same is true in the inverse direction. So one example of where this could help would be in two-view matching, where you would need to resolve the correspondence between these repetitive patterns. Another one is image retrieval. So the idea is that in image retrieval, one model is the bag of words model. So you have some descriptor, could be SIFT, could be anything, and you have basically quantized that descriptor to a visual word. And the idea is that if you have repetitive structure in your image, for example, bricks or windows or like facades, whatever, those will, of course, be overcounted. I mean, it's not discriminative in the sense that it doesn't discriminate it from other other images that have that same type of repetition. Like many images have bricks, many images have windows and so forth. So here's an example of this. We have some windows here and some basically building structure. And so there's a lot of matches between the query image and the match image. And they're different images, but we have a lot of similarity in terms of what's matched, and that's because what's discriminative about this image is not being matched. What's being matched is these repetitive structures, and so it's corrupting the image retrieval query. And we need some way to characterize these or deal with them either explicitly or maybe some distribution or something like this. But unless we can if we can't detect them, there's not much we can do. So I just want to speak a little bit about prior work. There has been some. Of course, there are constraints on repetitions through scene lines. So if you extract lines from the image, you can rectify the image and what's going on? Am I doing something wrong? Oh, okay. So we don't want to assume that there's any scene lines. So we would like to work on images where there may not be any such structure, any such lines could be, and I'll show you some examples of that. So, for example, we don't require this type of structured scene. Ours can be more general. There is an energy minimization approach, for example, that basically densely matches. It tries to find repetitions in the image by densely matching pixel regions, just basically finding the cost, characterizing as an energy between mapping dense pixel regions on top of each other and finding symmetries and reflections in the scene plane. It requires a rectification a priori so that you can do this matching. Well, we don't require that. And then there's the literature is quite varied. But the idea is that many of the previous approaches required some sort of assumption on scene structure, and we don't want to do that. So I'll skip ahead here a bit. So what is we take a local features approach, and I know a lot of you know this already, but I want to go through it because we'll need this particular construction. You'll see it again and again, so it's worth talking about. And the idea is that, well, you want to deal with occlusions, you want to deal with different types of scene transformations, so local features approach is a good way to build a scene plane from the bottom up and try to construct what is the pattern. Of course, when you see these things individually, you can't say that there's such a pattern, so we'll have to start at this low level and then construct the pattern, and that's sort of the idea of this talk. So what do we do? So to characterize repetitive pattern, we first get some discriminative, or we get a feature detector. In this case, this is called an extremal region detector, but there's other types, Hessian, affine, etc. So here's the contour of a particular extremal region, right? Now, once you have that contour of the extremal region, you can calculate the center of gravity, which is this cross, and points of high curvature, which are these 2 points. These are extremal curvature regions. So on this contour, we found these two high curvature areas, and we found this center of gravity. It turns out that these types of features are highly localizable, so they're repeatable, which is good. From that, we can extract local affine frames. And a local affine frame, a construction, is basically taking the center of gravity and connecting it to one of these extremal points, and then constructing, and then once you have that, so suppose so that's one of these like solid blue lines. I've just taken this and connected this guy. I transform it into this normalized coordinate system, and I find the right angle. So I have that guy, and then I calculate what's its right angle, and that's what this dotted line is in the unnormalized image space. So if I go back into, for example, this blue guy, in the normalized space, you can see the window there has been normalized to this guy here. And if I go back here, it represents, for example, maybe this guy with the dotted line, and then this solid one. So now we have a way to characterize this region that characterizes geometry. It turns out that these points are also transform covariantly with affine transformations, and all that means is that locally, basically, as the image is transformed, the features that we are extracting from these detectors are transforming covariantly with the image. And this is the process just illustrated in a different way. The contour, the construction of the affine frame, and then the region that's being described is characterized by SIF descriptor. So this will be used for appearance matching. Eventually, we will use this to match features based on appearance, and then this affine frame that I'm showing, these blue guys and pink guys, will be used for the geometry. So you see it's like highly engineered approach. So here is, for MSER only detector, here is an example representation. Once the, if this works, there we go. It's really sensitive.
Well, you should point it really to the receiver. And
Where is the receiver, actually?
somewhere there,
I don't know where it is, though.
where the notebook.
So maybe I can, yeah. Okay, I see. I thought maybe the receiver was over here, but all right. So there you go. There's the one set of MSERs, the local affine frames, and then there's the other set. Those are extracted. So that is basically how we'll start off doing this algorithm with that representation. So I just wanted to go through a little single view geometry just as a primer. So suppose you are looking at some reference plane. In that case, it would be this building facade. And your camera is here. So you have two coordinate systems, your camera coordinate system. This is your uncalibrated camera coordinate system. This is your global coordinate system. And this is the plane vanishing line. Now I've drawn it here actually in the image, but in this particular image I just kind of notionally drew it up here because that's where the vanishing line would be in this image approximately. So that line is really corresponding to that guy up there. So that's where this scene plane vanishing line would be. And the idea is this, like in computer vision we represent, so many of you are probably familiar with this, you have a camera matrix P. It's a 3x4 matrix that basically encodes the transformation from the global to camera coordinate system. And it has a rotation and a center, which is this guy, and this K is a calibration matrix, which is telling what the focal length is, and the center, the principal point of the camera. So this is the 3x4 matrix that is encoding this. But here we have a special case, and this is very important, because we can basically we have a scene plane, and so we can just say that the points that we're interested are on the scene plane. So we can say that the z coordinate is 0. So for example, here z equals 0. So in the reference plane, we have this coordinate being 0. So what happens is that when you do the projective transformation, when you apply this P matrix to a scene point, effectively this third column does not contribute to x prime, which is the projected image point. So it goes away, and it's equivalent basically to this, which is a 3x3 matrix, and this representation of the point, dropping this z coordinate. Now you have homography, 3x3 matrix, and you're operating not in the projective space P3, but the projective plane P2. So now we've made a difference in representation that will help us a lot. Okay. Okay, so now we want to do the affine rectification. So remember what the coordinate system looked like here. So this was the coordinate system, the uncalibrated camera. You have this x, y, and you have this vector going to the image plane. This is the z coordinate. Now we want to transform the coordinate system so we can do an affine rectification. So how do we do that? Well, the trick is this, is that you search for the vanishing line in the image. So that would be that, well, in this particular example, it was that green line in the original image that was going across here. So you search for this guy, and then you take the z vector and transform it so it's normal to the plane connecting the center of projection to the vanishing line. And that plane is also parallel to the reference plane. It happens to be. And that's done by replacing the third row of the camera matrix that you started off with the vanishing line. So this particular vector, which is normal to this plane, is denoted L infinity transpose. And that gives you an image that looks like this. Now certain properties have been preserved. Notice now that parallel lines are parallel. So I mean, when I say that, parallel lines in the scene are parallel in the image. And as you get closer to the vanishing line was up here, remember. As you get closer to it, the scene expands. And this makes sense, because as you approach the vanishing line, in this new choice of coordinate system, the z is vanishing as you project it onto that particular basis vector. And so when you do the perspective projection, when you divide by z, x and y will explode. In fact, if the vanishing line is really in the image, then there'll be points in the image that go to infinity. So the question is, how can we find this vanishing line? And this is one of the first contributions that I'll talk about. So here is a constraint, a linear constraint, that allows us to locate this vanishing line from repeated patterns. So the idea is a scale constraint for affine rectification. It's not derived here, but if you're interested, I can show you the paper. But the idea is this, that if you have these local affine frames, that in the scene plane, if you have something that's repeated, of course it's going to be the same scale. And the idea is that in an affine rectified space, this invariant is preserved, meaning that repeated elements in this space, any affine transformation that is applied to that will still preserve the scale. It's invariant. So what we do is we have these measurements of local affine frames that were gotten from our detector, and we say jointly they must have the same scale. And from that, which is not detailed here, there is a linear constraint that is derived. And so from a linear estimate, we can back out the line at infinity, the vanishing line. And so we can construct H by estimating L infinity from this linear estimator. So we can effectively get this guy. And then we construct H, and after we construct H, this image turns into this affine rectified image. So what if we want to go further? What if we want right angles to be preserved? So instead of, for example, just parallel, so we have parallel lines now where what were squares could just be parallelograms. We want to further get closer to what the scene plane actually looks. So what we're doing basically is in steps, we were reducing the ambiguity between the image and the scene plane. So we have an image of the scene plane, and what we really want to do is say, we want the thing to look as much like the scene plane as possible. We're essentially reconstructing the scene plane. So the next step is to so now we have this transformation. Now, it looks a bit different, and it's because it's the same, because of the invariant. So what I've done is we've identified this vanishing line through that prior linear constraint. Now we have this identity matrix up here, or this sub 2 by 3 has an identity here, and I said that any affine transformation preserves these invariants. So I just threw away those first 2 rows. I don't care anymore, because what I really care about is that these properties are preserved. And now I have it upgraded to an affine rectification. Any multiplication in these rows will continue to keep these invariants okay. So I just picked something arbitrary, and this is my first matrix. And now what I do is I need to find these guys. Now we search for A1 transpose, A2 transpose. This is an affine matrix. I want to find the affine matrix that will take those parallelograms, these windows, and turn them into squares. Well, preserve the right angles, so rectangles. And this is the next particular constraint I'm about to talk to will allow us to find these particular parameters. And what does it translate here to? Well, it's basically that particular. Once again, there'll be a change of basis, but instead of the basis, instead of changing this third vector, we will change these first 2 vectors. That's what the A1 transpose and A2 transpose. This, for some reason, this particular was not updated, so I apologize for that. So what is this constraint? Well, now we have our local affine frames, as you saw, like the measurements that we have, and now we're going to use congruency. The idea is that in the scene plane, if you know that something is repeated, then you know that the length extents of that object have to be congruent in the scene plane. And therefore, if we want to rectify this, we want to preserve these metric properties, we can use the constraint of congruency. In other words, if in the imaged space, there is no congruency. So if we take corresponding length extents, the blue to blue, and the red to red. So these are corresponding length extents. Something's repeated, maybe rotated, and now we take their corresponding extents and put them in the same origin. Then it will form an ellipse. It should really form a circle if the constraints are respected. Why? Because the blue should have the same radius. Once you're in the metric upgrade space, metric rectification, these should have the same radius. So what happens is that we search using these constraints. We've come up with a new linear constraints, or another set of linear constraints, to estimate the transformation that takes these ellipses to circles. It's very simple. In fact, you know how to do this basically once you have these measurements. So, and the same is true for reflections. So here's some rotated pattern, right? So we have something that was rotated, and now suppose we have something that's reflected. Well, once again, like I said in the affine rectified space, there might be some affine skew to these repeats. Well, we know that in the metric rectified space, they should map on top of each other, meaning that here is the axis of symmetry for this reflection. And there should be some in the proper space, we should be able to basically reflect about the axis of symmetry and have the corresponding length extents map on top of each other. And we search for a transformation that respects this particular constraint. Again, it's linear. So this gives us, if we have translated, now we have translated pattern, reflected pattern, rotated pattern, and we have a set of constraints we can use to reduce the ambiguity from image to scene. Oh, I keep doing that. So how does it work? So here's here's like an overview of what we just talked about. So here is the original image pattern. We upgrade it through affine rectification, and we notice that these guys are rotated. Say these red guys and the blue guys are undergoing some rotation as well. So we use our metric upgrade for rotations, and that was the original synthetic scene plane that I generated before I imaged it through some virtual camera. So we could upgrade to this. And so we've used those particular constraints to upgrade to this particular scene plane. Now, even if you get this far, there's still an ambiguity between your rectified pattern and the actual scene plane. In fact, it's a similarity, because you don't know the real how many centimeters these repeats are, for example, and you don't know how it's rotated and translated. So you have this particular ambiguity, but now you're very close, at least visually. It looks the same as if you were looking down at the scene plane frontal parallel. So how good does it work in practice? Well, this is, actually these images were sent to me by someone who was trying to compete with our method on a recent SIGGRAPH paper. So I chose to use these to test my method. And here's the original image. And here is the reconstructed pattern. Now, unfortunately, MATLAB is very bad at vector graphics, so at least exporting them. It's good, but it doesn't export them well. But these are all the local affine frames it found. There's just tons of them. This is also a testament of all the hard engineering over 20 years that these guys did to accomplish such a thing. But you can see the reflections here. You can see the rotated features going all the way around, like these guys on the rim even. And these are coplanar. These are some mistakes, but barely, meaning that these are not quite coplanar, but it's almost a scene plane. So these were things that were picked up by the method that were also considered coplanar repeats. They are repeating, but they are a little bit off the scene plane, for example. And I would like to say that here you get into a very difficult estimation problem, which I won't talk about, which is that in order to construct these repeats, you need to know how they map on top of each other. Think about all the different rigid transforms that are existing in these particular set of repeats. And that's being estimated by the algorithm, all the different types of transforms to map one repeat onto another. And this is the rectification. Here is a cathedral. Again, the reconstruction, so the rose window is very well preserved there. You can see some rotational symmetry there. There's reflections, and even here along the details. And this is one pattern here, but then we have all these different translated patterns as well. So for example, some translations down here. So we have multiple different pattern types, multiple constraints at play. And here's the rectification of that facade. So these were a bit synthetic, so I wanted to show you something. This actually is a difficult one a bit because the features on this are surprisingly bad, at least with the detectors I was using. I think partly because of the specular reflection and on the side of this, so we don't get a lot of good matches. But still, it's not bad. So rectified fire truck. By the way, you can see some nonlinearity here, and I'll explain that in a second because I'm actually estimating lens distortion as well in the model. But we haven't talked about that. This one was also sent to me, and it's actually a difficult one because it was sent to me on purpose by the guys who wanted to write this paper because you have all this background noise. So he was trying to break the local features. He chose this on purpose because local features are going to go crazy here. They're going to get tons and tons of matches. Furthermore, this is not an exact pattern. This is a non-rigid object, right? So you have even the fact that the repetitions aren't exact. You can see that it's not really repeating, that colors change and so forth. So the fact is, though, is that the way we've developed the algorithm, we have a generative model for it, which I haven't talked about yet, but it tries to pick the most correct pattern and project it into the image, or tries to infer the most correct pattern and check in the image. So what it's actually going to do is going to fix this in the inference, and then project it in there and estimate the rectification. And so we get this result for the features. So you can see there were some mistakes a little bit on the noise, but still a lot of it inside the pattern, and you get a rectification. This is another example in Wrocław. This is just a bunch of building facades, and of course the repetitions are completely different than in terms of their frequency and distance and so forth. And we get pretty good coverage, and we're able to rectify basically the entire row of buildings. So I wanted to show an application which is these KitKats are repeating, of course. That's what's used to estimate the repeats. And if you're able to identify the repeat, you can also segment them. So you can use graph cut, you can use any sort of segmentation method, and you can get fairly precise segmentations of the repeated object. So you can extract that from the image. And that's the that's the rectification. And and this was put there on purpose because it allows me to measure the right angle, just to see how it's doing. So I wanted to speak now about the generative model that we infer to actually do this. And I think the reason why I have this slide is it's useful for interpretation purposes, and even when generating an evaluation metric, it is also useful. So the idea is this: we have some camera matrix, as we discussed in the first slide. We have some camera matrix P and some scene point X. This is our scene structure. But it reduces to, as we showed, a problem in P2, which is this homography and this representation of the scene point X in P2. Now, one way you can look at it then is that this part is the rectifying homography. So remember, H could be estimated through the affine rectification with the scale constraint, and A either by one of the congruency constraints. So this is what will rectify. Sorry, there should not be a prime here. That's a mistake. But this will estimate the rectification. So what we do is we, quote, reconstruct the scene plane, the pattern, and then we have a camera, which is the inverse operation, that views it. So it can be almost looked at, and it's sort of the interpretation we use for the generative model, as a reconstruction problem. We're actually reconstructing the plane in an affine space, or in a metric rectified space, and we're viewing it with some camera. So so I remember we had the SIFT descriptors, and I just wanted to talk about how we initially in order to start building the pattern, we need some labeling. You can think of it as you could solve by even a discrete optimization problem. I've tried this. The idea is that for each of these local affine frames, it has a descriptor associated with it, and you want to label them such that they are tentatively grouped together. So this is just grouping by SIF distance, for example, and you get some tentative grouping. Now that you have that tentative grouping, you're going to start building the pattern. But one point I just wanted to point out the difficulty of it, because you have to have some representation for the pattern, right? You're going to build some model for it in this rectified space. But what's your representation? Because it's non-unique even from, like, if you think about it in information theory or coding. The idea is that how will you print the pattern? Suppose you had a stamp. Would you choose, what would you choose? What partitioning would you choose? Would you reflect this guy? Or where would you choose your boundary? Maybe this guy and then try to reflect it? Or the idea is that it's non-unique and it's not particularly trivial, because even if you think about it hierarchically, you could start off with this guy, print, 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 and then maybe start with him, reflect, and then you have to reflect this little guy here, and then build this one and reflect. And so you have to create some atomic stamp for it and sort of build it from that. That's the challenge. And so, of course, I didn't solve that problem. I think you can only solve it in an approximate way anyways. But we came up with something reasonable. I'll keep going. So that's the idea of motif construction, is that you come up with some stamp that you can print the pattern. So what is a generative model? The idea is, as I showed before, that we want to generate some image pattern. Basically, we want to print a pattern in this rectified space. So the idea is this, that we start off, as we did, we start off with some distorted image. Here I emphasize the lens distortion, but we start off with some image scene plane, as we did in the beginning of the presentation. And we go backwards. We rectify, and then we get some estimate of how to print the pattern. So now we've basically got an initial guess for what the pattern looks like in a reconstructed or rectified space. And then what happens is that we go the other way. Now that we have some estimate of the pattern, we can print it into the image using the geometry. And this allows us to formulate a maximal likelihood problem. So we have how the entire pipeline of imaging, and this from once we have some initial guess, we can basically go forward and say we have some pattern in rectified space, and then we print it into the image, and then we compare it to the measurements. The measurements were those local affine frames that were extracted, and we maximize the likelihood, which is essentially the square distance in this case, between what's printed in the image and what the measurements are. So here's an example of one particular printing. This is one repetition type, and they're color-coded. You can see the original measurements that were extracted, and then here is one choice of how it was printed. And then there's a segmentation that was used. We segmented the pattern based on those features. What was interesting is that we have, what is this, like a 8-fold symmetry, 1, 2, 3, I think. And we don't get this one because we didn't get, for some reason we didn't get any features from the feature detector. And so it actually didn't segment that part because this is a 5-fold symmetry. Some cows in an airport, another segmentation example. And this is multiple patterns, for example. So, okay, and I wanted to, before I conclude the talk, because it's about over, I wanted to show you a recent result. This is a result that we just had maybe 2 months ago with the colleague Susanna Kukelova. And this is using similar constraints to estimate the vanishing line, but now we're also in this pipeline estimating in the initial stage of the solver the lens distortion. And I wanted to show you what is possible. So I'm already showing, by the way, this particular result is using a minimal sample. So what you're about to see has no optimization other than the minimal sampling. So basically 2 pairs of these local affine frames were sampled. So that's 6 points, although we don't even use all 6 points. 6 correspondence is what I mean. And we are able to get a result like this for the lens distortion. So just from that few points, we can pretty much resolve the lens distortion and then affine rectify with lens distortion. You see this thing here, by the way. You see how it's cut off. Remember I said if the vanishing line is in the image, then it will go to infinity. So the vanishing line is right around here, and then I backed off a little bit and just cut it off. So when I was rectifying the image. And you can see that the lens distortion is corrected fairly well, and now parallel lines are parallel. And that was just from a few points, correspondences. So this is, and also sampling. Of course, we sampled these point correspondences. I won't make the sound effect. I'm tempted to. So, all right. So, thanks for your attention. I just wanted to give a talk about how some very simple geometric constraints can do some cool stuff. And yeah, that's it.
Thank you very much. We have time for questions. Can you hear me? Okay. I have one question here.
Hi, thanks for really cool speech. It's awesome. I just like to ask, what is the estimated speed of such solution? Because it can figure out how to correct our lens distortion. Can it be used in some IoT devices or something like this in real time?
So that's good. That's a great question about speed. It depends on the number of features extracted, because there can be thousands of features extracted with these detectors. So it's really, of course, depending on how much texture, but it can be quite fast. The problem here, so the two big time components are, of course, the sampling to find some initial linear estimate for the rectification. And the second big time component will be the Levenberg-Marquette, which is that maximum likelihood estimate. So I mentioned that to get the high quality solution, we are basically printing the pattern from rectified space into the image, and we're optimizing jointly all the parameters. So that includes lens distortion, which is global, rectification, which is global, but then local to the pattern, we have all the rigid transforms. For each local affine frame that you saw, all those hundreds of features, there is, for each grouping of them, there's a rigid transform associated, so you have a rotation and translation associated with that. And so those are all being jointly optimized, and you can sparsify it, but in terms of how fast you can actually make it with like a sparse Jacobian, etc., it's doubtful that you can make it real time. Actually, probably the augmented pixel guys would know this, because it's something that they do. I assume something like this anyway. So, yeah. I don't know if that didn't really answer your question, but so for like, let me give you an example. For like the KitKat, it's on the order of tens of milliseconds, which is quite fast because there's not that many features. For like that circular window with tons and tons of features, you're talking maybe 15 seconds in MATLAB, but it's not optimized for speed. So.
Okay. Second question.
I also have considered the problem for rectification images like that, and I read an article. There was used SVD decomposition for solution. So image considered like matrix for SVD, and then a minimization of singular values, and this gives not bad solution for found parameters for rectification.
Yeah, so is that your question?
Have you considered this solution?
Well, in fact, we do use SVD. In fact, we use a very similar technique. So the affine rectification and it's a least squares. It's more Penrose inverse. But for the metric upgrades, those are SVDs, as you say, and they are giving the parameters for the affine correction. And in fact, we have this decomposition, right? We've decomposed the rectification into an affine correction and a metric upgrade, and both parts are solved linearly, as you suggest. So it's very similar to what you're saying. Is that answering your question, I guess? Or, okay.
Connection between SVD and I'm just interested, have you considered this approach for your solution? And because I have seen pretty well a result for rectification and found periodical structures, we are just applying SVD for original image.
Well, I don't. Well, in terms of original image, SVD of the original image.
Yes, SVD of original image or some parts of this image, and finding of singular values gives dependency of lines of periodical structures on or any structures among the lines, and this gives some information for discovering of periodicals or dependency between image parts.
Well, I think if I understand your question correctly, let me make 2 points about SVD. So we're using local features approach, and you're talking about a dense approach, I think, for the entire image.
Yes,
Yeah,
dense approach.
Okay, that's now I have you. But let me make a comment first on the local features, and then I'll address the dense approach. By the way, SVD is, so you're doing a totally square solution. It's an algebraic error. Like these constraints are projective constraints or affine constraints, and you're basically minimizing some algebraic error which doesn't have geometric meaning in the image, although it works. It works quite well, and it's often done in computer vision where it's called discrete linear transform is one example, for example. So you're using, the idea is that you first try to make a guess at the pattern using these minimizers that are minimizing some algebraic error. And then once you have some guess at the pattern, you put it back into the image in the forward direction, and then you maximize the likelihood. So that's one comment about the local features with SVD. Now, the technique you're talking about is probably called tilt, which I think is where it's about the rank minimization of an image. So the idea is that if you treat the image densely, as in just say an array or a matrix, treat the image as a matrix, a dense patch, then the idea is that the rectified version of that image will have a lower rank. And so it's doing rank minimization, and it's minimizing the rank by finding some transformation, a homography, to minimize that rank. And I think they even do it for metric upgrades as well. And we have compared to that method. The problem with that method is that since it's dense, it can't handle occlusions very well, and the area has to be annotated by somebody. So someone has to go in and say, I want this area rectified. It can't. The rectification can't be discovered because it's taking the entire dense patch and minimizing the rank to get the rectification, basically.
Thank you.
More questions? Okay.
How do you segment those cows with the features you extract?
Segment the...
No, cows or whatever.
Yeah.
The symbols.
So that's well, you can even treat it a bit like a black box. So because, well, this is one nice thing about this method. Since you have localization of the pattern, once you've discovered these local features repeating, you know where the pattern is because it's giving you the location of those features. So you can statistically sample that region around that local affine frame, or even in the convex region. Just make a triangle out of the local affine frame. You can have some model. Maybe it could be a graphical model, it could be anything, and then you just plug it into a segmentation algorithm, because now you have a concept of what is interesting and what is not interesting, because the local affine frames give you where to statistically sample example, to build a model. I used one of my colleagues' segmentation algorithms. I don't even know how it works. I just fed it the locations. But I could imagine using GraphCut, for example, to segment the pattern from the background, because you could just build a foreground model from the sampled locations of where these local affine frames are. Does that answer your question? Yeah. Okay.
Thank you. I have a question. If you have only 2 occurrences of a pattern, and so you can have as low as like 6 points, I guess, reference like centers of mass and corners. So how stable is this rectification in this like case when you have like only 2 repetitions?
That's a great question, because, so you're right, there's 2 pairs. So for this framework, by the way, all the way from the beginning, the minimal sample size is 2 pairs of 2 of these local affine frames. So it's data dependent in the sense that if your pairs of local affine frames are spread across the image, then it will characterize, the noise won't affect so much the estimate. So if they're close together, you're in trouble. You will get a very good rectification in that one little spot, but then towards the corners of the seam plane, it'll be warped a bit and so forth.
Thank you.
More questions? Okay. I see you're tired. So thank you very much. Yeah, make a poll.